Okay, guys, in that example, we took the concept of the probability of A and B equaling the probability of A times the probability of B. Sorry, that line's not big enough for that. And we changed it to, in both of those examples, really, the probability of A and A and A, and we just kept going. So it was the probability of A times the probability of A times the probability of A. And we kept going using exponents to make our lives a little easier with the calculator. Here's one, instead of with 5 or 6 different events being the same, here's one with 200 events being the same. It's another example from the book, and I do actually want to go over this one together because the wording, I think, could be a little tricky for you guys, so I want to make sure that we talk through it together. Do I have that so you can... I'm just going to read it out loud anyway. Many people who come to clinics to be tested for HIV, the virus that causes AIDS, don't actually come back to learn the test results, which is a little mind-boggling. But I know that, like, when we got married, we had to take certain kind of tests like that, and I mean, we knew what the results were going to be, so it might just be the case that people take the test and go, I already know what it is, but you're making me take this test, so I don't care to go back on another day and get my results. Or it might just be a weird thing where people get the test taken and then are nervous and don't want to know the results. I don't know how that happens, but clinics now have a rapid HIV test. Well, that should sound familiar with our present day situation. Rapid tests coming up. They give a result while the client waits. In a clinic in, I think that's pronounced Malawi, but I'm not sure, use of rapid tests increased the percent of clients who learned the results from 69% all the way to 99.7%. So just the speed at getting the results back increased the people who knew, which I think is kind of an important thing for society, all the way up to 99.7%. Now, the trade-off for fast results is that rapid tests are often less accurate than slower lab tests. Applied to people who have no HIV antibodies, though totally healthy, one rapid test has a probability of about 0.004, less than 1%, less than 0.5% of producing a false positive. A false positive means it says, hey, you might have this, and you don't. If the clinic tests 200 randomly selected people who are free of HIV antibodies, what is the chance that at least one false positive will occur? At least one false positive will occur. That is a more complicated question than the ones we've been answering. Assume that the results for the different individuals are independent. So I don't know how long it takes them to test 200 people. Maybe that's a month. Maybe that's a year. I mean, I really have no idea how to even take a guess at that. But 200 times. So what we mean here is that we would have one person who, let's see, what's the probability that at least one false positive. So that can be the at least we got to talk about. That could be an easy problem or a difficult problem. See, if we try and answer this straight up, we would have to find the probability that there's one false positive and 199 correct negatives. And then you'd have to put an or, so add this next scenario, 2 false positives and 198 negatives, and 3 false positives and 197. There would be 200 sets of probabilities that we would have to go find and add together. But here's how you do a problem like this. If the problem is, what's the probability that at least one false positive will occur? You got to think about the complement here. What's the only way that can't happen? The only way you can't have one false positive is to have all of them be negative. And how do you find complements? You do it with a 1 minus. So look what they do here. They find all negatives. And if there's a 0.004 of getting a false positive, subtract that from 1, it's a 0.996 that they would come up negative. If they don't have it, it's a 99.6% chance that the test comes up negative. So we would multiply that times itself 200 times to find the probability that all 200 of them are negative. And you get 0.4486. Now, what you got to do with that, because that doesn't really answer the question, is we have to do a 1 minus 0.4486 to get the probability that at least one is actually a false positive. Okay, so, and whenever you're asked, and we're going to write this down in a minute, the probability that at least one of something happens, it can be very difficult to get that right, approaching it straightforward. So what you do is you go 1 minus the probability that it never happens. That means all of them are the same. They're all negative. So 0.996 to the 200 is 0.4486. And then we do 1 minus, and we get 55. By the way, if you're going to test 200 people, and the probability of this false negative is 0.004, that's great when it's just one person. But when you got to be right 200 times, there's only a 55% chance. A 44% chance that we get it right 200 times. So there's a 55% chance that there's at least one person who gets told, hey, you might have this virus which causes AIDS, when they don't. That's kind of a bad day. Okay, let's go to the next page. So I want you to remember this trick. This is the 1 minus trick, all right? Complements go like this. I'm going to write complements, and I'm going to say the probability of A complement, you've seen this before, is equal to 1 minus the probability of A. We're going to use that kind of in a bigger sense here, okay? Anytime you're asked for the probability of at least one of something, it doesn't matter what it is, probability of at least one. It can be a really difficult question to answer. Instead, use the complement rule. I want you guys to train yourself to look for that phrase before you take this test on Chapter 4. Definition: the probability of at least one, regardless of the context of the problem, is always equal to 1 minus the probability of none. Okay? Let's say there's a family and they want to have, they're going to have kids, right? We're going to have a big family. We're going to have 5 kids. What's the probability they have at least one girl? Okay, 5 kids, at least one girl. So that would go probability at least one girl. Well, here's the problem. You'd have to find the complicated problem. You'd have to find the probability of having 1 girl and 4 boys, 2 girls and 3 boys, 3 girls and 2 boys, 4 girls and 1 boy, 5 girls. And you'd have to add all those up because they're mutually exclusive situations. But finding the probability of 3 girls and 2 boys isn't as easy as it seems. So instead of all that complicated mess, we would just go 1 minus the probability of all boys, because it's the only way to not have at least one girl. And so the probability of all boys, well, that's 1/2 for the first one to be a boy, 1/2 for the second one, 1/2 for the third one, the fourth one, and the fifth one. So this is 1 minus 2, 4, 8, 6, 132. So that would be a 3132, whatever that is as a decimal. 3132 is the percent chance, if you're going to have 5 kids, of having at least one girl. It's a 96.875% chance. Okay? Book problem, do number 6. Why don't you guys go to page 307 now and do number 6. It should be very similar to this, and we'll check the answer in a minute.